Welcome to the Explainer. Today, we're doing exactly what the title says, demystifying that super familiar black and white striped rectangle plastered on literally everything we buy. We're going to break it down in detail, but in really simple words, so we can finally decode the invisible language of barcodes.
I mean, think about it for a second. Have you ever wondered what actually happens when the checkout scanner goes beep? You just grab a box of cereal, wave it over a little glass plate, and boom, instantly the system knows exactly what you bought and exactly how much it costs. Okay, let's dive into this because the technology making that everyday magic happen is surprisingly elegant. It's actually wonderfully simple to understand when we just peel it back layer by layer. Section 1, the Everyday 1D Grid. So just to set a clear baseline here, think about the codes we interact with all the time now. We're all super used to pointing our phone cameras at those 2D QR codes, right? Now, those work in a two-dimensional grid, meaning they hold complex data that travels up, down, and straight across. But traditional barcodes, specifically the linear or 1D barcodes, like the UPC code you see on your groceries, well, they work in just one single dimension. Because of this, the scanner's laser only really needs to read straight across, one horizontal plane, just zipping from left to right, picking up a simple combination of parallel lines and blank spaces. Moving on to Section 2, Anatomy of a Barcode. Now, what's really interesting about this is that while a standard barcode might just look like a totally random cluster of messy stripes, its structure is actually incredibly disciplined. Every standard barcode follows 4 strict anatomical rules to function properly. Let's explore these simple components. First up, we've got the quiet zone. It sounds kind of dramatic, but it's really just the solid white space on the far left and right ends of the barcode. Think of this exactly like the blank margins on the page of a printed book. This margin tells the scanner precisely where to start looking, so it completely ignores all the colorful background text, the branding, or any other images printed on the packaging. Next, we have these starts and stop guards. These are those specific, highly recognizable thin patterns of lines sitting right at the very beginning, the very end, and often smack in the center. Basically, they serve as anchor points. They establish the barcode's direction, letting the scanner know exactly which way it's facing, and they establish the baseline timing, which is absolutely crucial because the scanner needs to know exactly how fast to read the incoming lines. And then we get to the real meat of it, the data characters and the human-readable text. Those varied bars right in the middle, those are the data characters. They hold the actual encoded information. But underneath those bars, you'll see those familiar printed numbers. Actually, it's pretty important to note here, the scanner ignores those numbers completely. Yep, they are purely just a human backup. You know, just in case the barcode gets crinkled or damaged and the poor cashier has to manually type the whole thing in. All right, Section 3, the binary secret.
Okay, so to a computer brain, the code is really just binary data. But instead of reading the color black or white directly as a single digit, the scanner is actually measuring relative width. The whole system is divided into these tiny, almost microscopic building blocks called modules. So, explaining it in simple words, a scanner reads a dark module as a 1 and a blank, light module as a 0. Simple as that.
And this brilliantly illustrates the core trick of barcodes. A thick, chunky black bar, it isn't just one bar. It's actually several tiny dark modules stacked right next to each other, perfectly merged together by the ink on the paper. Because of that, to the scanner, that thick black bar doesn't look like a solid rectangle at all. If it happens to be 4 modules wide, it registers literally as a string of ones. 1, 1, 1, 1. Now, the exact same logic applies to the blank spaces on the sticker. A thick white space just represents multiple light modules. It is so easy for us to completely ignore the blank paper, but that white space is just as critically important as the dark black ink. Likewise, if there's a wide gap between 2 black lines, the scanner sees that gap as a straightforward sequence of zeros. So a gap that's 4 modules wide translates directly to 0, 0, 0, 0. So by simply varying the width of those thick and thin black and white stripes, we're building a precise sequence of ones and zeros that perfectly represents your exact grocery item. In the standard UPCA system, which is what we literally use on retail products globally, each number from 0 to 9 is represented by a unique 7-module pattern of these alternating bars and spaces. Pretty clever, right?
Section 4, from light to logic.
Let's move to how this builds, because when a laser or an LED scanner sweeps across those printed lines, it triggers a wildly rapid 3-step conversion process. Step 1 begins with light absorption and reflection. Think of it kind of like shining a flashlight into a pitch-black room. The scanner shoots this intense beam of light right at the barcode. The black bars absorb that light, but those white spaces, they act like tiny little mirrors, bouncing the light right back into the scanner's internal sensor, which is called the photoelectric cell.
Next up, in step 2, that cell translates the bouncing light into electrical waveforms. When the cell sees a bright, white space reflecting a ton of light, it generates a high voltage. But when it hits a dark, non-reflecting black bar, the voltage instantly drops to low.
Finally, in step 3, the scanner's internal computer kicks in. It rapidly measures those high and low voltage pulses. By precisely tracking how long the voltage stays high or low, it instantly reconstructs our sequence of ones and zeros, perfectly matching them to the exact product waiting in the store's massive database. And that all happens in the blink of an eye.
Section 5. The built-in safety net.
So here's a really interesting quirk. Traditional barcodes actually don't have robust QR-style error correction. Basically, if they get too smudged, they just fail to scan entirely. So the crucial point is that they instead use a built-in safety net to prevent incorrect scans from happening in the first place. They do this using what's called a check digit. This is a special mathematically calculated number sitting all the way at the very right end of the barcode, and its value is based entirely on the digits that came right before it.
It basically works like this. The scanner performs a lightning-fast internal calculation on the first 11 digits it reads, multiplying some numbers, adding others together. Now, if the result of the scanner's quick math matches that final printed check digit on the package, the scan is totally approved. But if it doesn't match, it immediately beeps an error tone. This brilliantly simple math ensures that your slightly squished box of cereal is never, ever accidentally rung up as an expensive flat-screen TV. We can all be thankful for that.
And there you have it, the whole shebang. The next time you're standing in line at the store and you hear that super satisfying beep, you're going to know exactly what invisible binary language is being spoken right in front of you. But it really makes you wonder, how do your local inventory systems actually take these simple, elegant 1D codes and use them to flawlessly track millions of products behind the scenes? Are you curious to look deeper into massive global barcode standards like GS1 or Code 32? Keep asking questions, keep looking closely at the invisible details of the world around you, and I absolutely cannot wait to guide you through our next explainer.